Good morning, everyone. In this presentation, we're going to talk about harmonic balance for external applications. So, usually harmonic balance has been used inside the SU2 group for turbo machinery, but there are some works around, especially from Glasgow University, where it is used for rotorcraft and propellers. And these are matters of interest in our research group. So, let's say that our target is to use this reduced order model to compute the acoustic field generated by propellers and rotors and introduce it inside high fidelity optimization in a more convenient way with respect to a fully consistent approach that has been already developed. So I don't want to go inside the details because this has been developed by the task group. So you can ask to them the mathematical details, and I want to say anything stupid. Harmonic balance is a thermospectral method where the frequency that we are going to solve don't need to be multiple integers of each other. It has the advantage in respect to other spectral methods that can be easily parallelized. Just remember that we are going to solve k frequency, and what we are going to obtain as output are n-time instants inside our period of oscillation or rotation, and this n is equal to 2k plus 1. So what we obtain through the mathematical passages is n steady states that involve in pseudo time a torque through each other through the harmonic balance operator, basically. So harmonic balance for air acoustic. Inside SU2, in collaboration with Bristol University, we have developed this acoustic module that has an FWH formulation. What is used for? It computes the pressure oscillation perceived by some observer that are positioned at a certain distance with respect to the body that is rotating or pitching. In detail, we implemented this formulation, which is the differences Antonio, that can use also permeable surfaces. The details will be shown by Professor Beckett this afternoon in a presentation, and the code has been validated and verified thanks to the experiment conducted in the wind tunnel of Bristol University, specifically for propellers. So what I propose today is why we don't use harmonic balance for the direct simulation, since it gives you advantage in terms of computational time. What we obtain are these n-time instants, but for acoustic, we need a more time-accurate solution. And so we're going to do Fourier interpolation for the surface solution in each node of the surface. This has been implemented inside the T-output legacy, specifically in the method special output harmonics. And then we take this solution and we give to the acoustic module, and it's going to compute the sound pressure level perceived by these observers. What are the advantages? Let's think about rotorcraft in forward flight. At each iteration, we need to rotate the grid and deform the grid, and it is time consuming. Instead, with harmonic balance, we have to do this only n times. And since it is a spectral method, we don't need to simulate the physical process period. So the first test case that is proposed by the SU2 community for harmonic balance is this pitching high coil in transonic condition. I have to say that the amplitude is really low. So the harmonic balance solution has been performed with 3 frequencies and 5 frequencies, and then being compared with a fully time-accurate Uran solution that takes 200 time steps per period and 10 inheritors. It takes 6 periods before reaching a periodic solution. So if we compare the aerodynamic coefficients, it can be seen that 3 harmonics are enough to almost well capture the history of the CD. But since I want to do acoustic, we need to know that the pressure oscillation in each point of the solution is well captured. And so if we go closer to the trailing edge, where the flux becomes more complicated, it seems that we need at least 5 frequencies to well capture the pressure oscillations. But FWH is not for 2D, we need a 3D formulation, a 3D object. So I just obtained a straight wing of 3 meters span and positioned this 70 microphone in the upper part at a distance of 10 times the chord. I changed the slit, the free string conditions, so there is no angle of attack, but I increased a lot the amplitude of oscillation to make things a bit more interesting. And here you can see again that probably 5 frequencies are not enough to well capture the CD history, but We don't see this in the SPL. So here we are comparing an integral information about the pressure oscillation per seat by the observer, and the relative error between the harmonic balance and fully time-accurate solution is lower by 1%. And I can say that the computational time is really reduced. So our interests are propellers for urban mobility. This is the Polimitas case inside the Gauteo AG26. We are in forward flight at J0.8. The Mach tip is around 0.3, and it has been simulated for five frequencies. I removed the nacelle just to reduce the dimension of the grid. An experimental campaign has been conducted in Politecnico, and so we can compare the thrust and the CP also with experiments, and we obtain a really good agreement. And I'm reporting also the CP plot at 75% of the blade radius, and they really well matched. And also again, the SPL show a relative error under 1%. But we all know that integral information can hide some errors, so it is better to watch at the history of the pressure oscillation. So total noise is split in two components, loading term and thickness term, and they both well match. And this is not so expected for the loading term, especially. And the second figure that you can see is the absolute error for the directivity spectrum. So if you go in one direction, you have the spectrum of one of the 70 microphones that I showed you before, and I'm reporting the absolute error, which is 10 to minus 5. So really good match in the entire spectrum. But let's talk about optimization, which is one of the focus of my PhD. Okay, so I propose this optimization chain. If you look at the work of Professor Colonna, they used a fully consistent optimization chain where harmonic balance is differentiated also for the discrete adjoint. But my concern is virtual memory allocation, because the memory allocation with harmonic scales linearly with the number of frequencies that we are going to solve, and we all know that with directly differentiation, also in that case, the virtual memory is augmented of 3-4 times. So combining these two effects, my concern is if we need to simulate a very big grid, maybe RAM is going to be a bottleneck. So while we don't use harmonic balance for the direct simulation, we do the interpolation of the coefficient to obtain the real history of our objective function, and then we feed this n-time instance inside a standard U-runs discrete adjoint. So basically, we are bringing to extreme a temporal coercive technique that has been proposed by Tom and Beckett years ago in this paper, where we show that with unsteady adjoint, you can use less than instance respect to the direct simulation to obtain a good sensitivity. So just to recap, when we talk about optimization, it means that we want to minimize an objective function, and the first constraint that we impose is our flux result. So in a fully consistent adjoint framework, we would have this equation, which is the one that we obtain from harmonic balance. Instead, here we are using the standard dual step of SU2. So again, I repeated the test cases that I proposed before, and here I report the sensitivity obtained with harmonic balance with 5 frequency and very steady for the top design variables of this airfoil, and they really well match. And so what is happening is that the history of the optimization is really similar, and we obtain the same final state. I stopped the optimization just after 10 loops of optimization, because like fully unsteady optimization, it's really time consuming. And so here you can see how these small changes on the surface has a huge impact in the Mach field of this airfoil, which is preaching. And this is the time that took to do the joint step if we used only the n-time instance from the harmonic balance, which is 70 minutes on this core, on this CPU with 16 cores, and this is a fully time accurate. So you have to think that you have to repeat this for each objective function that you take in consideration, also for like the lift constraint that we have here. So a more challenging test case, we are in 3D. This time I decided to solve all the equations just to reduce the computational time, and the optimization has been performed only with the framework that I just proposed. So we obtained this reduction of the CD inside the period. After 10 loops of optimization, I took the baseline and the optimal shape and repeat just that simulation with the fully time accurate solution. And the error between harmonic balance and the fully time accurate increases for the optimized shape, but we can see that confirms the reduction of the CD. And here is how the shape is being modified and how the Mach field is slightly impacted. So I think that we can start to use harmonic balance also for external aerodynamics, and it will give you good results in terms of FPL and spectrum, but you need to increase the number of frequencies that you would use with respect to just obtaining the CD and the CI, basically. And we showed that for the 2P test case, it obtained the same path of optimization, and the computational cost is strongly reduced. I still have this open question if this is possible also for helicopter blades. I have some preliminary results about the Car2 test case in Dover, but I'm having big difficulties for making it converge for forward flight. So, thank you for the attention. I hope you were interested.
So, two questions. First one, which version of the
7.4 when we developed the FPH.
My second question is that probably showed what if you get with the comparison between the memory cost between the base optimization and the other one, what's the gain?
So this is virtual memory allocation, and this is the CPU time. It is a profiler called the heat track.
We can't feed the device.
So I think this is slightly higher in the hands. Yeah, because it is increasing with the number of times that what you solve with the standard. It is the
Same order.
Yeah, same order.
Same order.
For this test case, yeah. I like the advantage in terms of computational times increases a lot with the 3D test cases, especially when you have to perform the grid, of course, for that simulation. And I will do some profiling also of that in the close future.
Are there any plans to move some of this ability to version 8? I know cities the ability output and exist.
Yeah, of course, we can bring it to source A. Like for the optimization part, everything is already there. It's just a modification of the Python. Okay. And yes, for the part of interpolation, you can bring it to version 8.
What about the force winning Hawkins and access for the entire SU2 community?
Where?
I'm asking since very long if we could get the force winning Hawkins in the latest central version. Well, especially institutes which finance this in the past for very long.
It's a model that's in common between Hasa and Horizon, but we have to work on it for the home part. You have to work with customer and customer.
Yeah, this is another aspect.
Actually, we worked on the packet and finalized how we incomplete versions. It's not back in SU2, so we gave it to back, it's open. We can.
That's not in the latest.
It's not in the latest. Yeah.
But nice.
But then we can push that.
So, have you thought about going the other direction? So using fully activated for the final event on mouse.
No. No, I don't know about it. Yeah, it's not a form of work. Or you should actually less than that for the choice. And so that's how I feel. was a curiosity that I wanted to investigate.
Would also be interesting. Keep with that. I mean,
What you said,
you're running the session.
no, no.
Do you have any converging systems when you do this transformation to the full net history? Because that's something typically that you will need a very convert final on the listening product.
Well, it's really difficult to make harmonic balance converge for external aerodynamics.
Yeah.
There are just a few papers that talks about the stability of the numerical number, and gave me a lot to find them. I can send it to you in the really low result.
Yeah.
And also the cockpit has to be closer to the body with respect to a standard simulation. But once the harmonic balance converges, it converges really well. So or it does not converge or converges really well and really quickly. There is nothing in the middle of what I can see.
Okay, thank you.